Hello, welcome dear students. Welcome to the TEQIP Faculty initiative of Let's Crack the Gate. So, welcome to the module 2 of Power Electronics series on phase control rectifiers. So, let's begin with the today's lecture. So, till now we have studied so far about the single phase, half wave, controlled and uncontrolled rectifiers with various types of loads such as R load, RE load, RL load, RLE load, C load, pure inductive load and so on. So, now we are beginning with the next topic, that is single phase full wave rectifiers, controlled and uncontrolled. So, today's topic is single phase AC/DC rectifiers, controlled and uncontrolled. So, let us begin with the first uncontrolled rectifiers, because when we understand the working of this, then we can easily understand the working of controlled rectifiers. So, first topic is single phase uncontrolled rectifiers, single phase that is full wave. One thing it is missing, it is full wave. Yes, single phase full wave uncontrolled rectifiers. So, as the name suggests, these uncontrolled rectifier means they are containing the diodes as their single phase means as their switches. So, when we talk about the single phase either controlled rectifiers or uncontrolled rectifiers, we generally have got two configuration in it. First configuration is called this midpoint type, and in short they are also known as M2 type. Why it is 2? M means midpoint and 2 means 2 pulse. Alright. So, please note that prior to this we have studied about a single phase half wave rectifier, whether controlled or uncontrolled. Those rectifiers are known as single phase 1 pulse rectifier. So, what is that pulse? I will just explain it. And another type of rectifier in full wave is bridge rectifier. Bridge rectifiers, and they are also known as B2 type of connections. Alright, so these are the technical terms. So, now let us come what is meaning of 1 pulse and 2 pulse. It is very simple, that if we have got input sine wave like this. So, in one input cycle, let us say if it is Vi input. So, in one input cycle, whatever number of output cycles you are getting, that denotes the pulse number. Suppose in a half wave rectifier, so for one input cycle we get only one output cycle. So, see here t is also 2 pi and here time period is also 2 pi in both the cases. That is why it is called 1 pulse rectifier. Alright. But when you talk about the single phase full wave rectifier, what you will get here, that for a single phase input sine wave input, what you will get here, it is like that, means like that. So, in one input cycle, that is 2 pi, time period 2 pi, you get 2 output cycles. Alright. So, here the time period is pi. So, here in one input cycle you are getting 2 output cycles. Alright. So, that is why it is called 2 pulse. Similarly, when we move to the 3 phase half wave, there we see that for one input cycle we will get 3 pulses as output. So, that is known as 3 pulse, and when we will go for the 3 phase full wave rectifier, there we will see that for a one input cycle of input sine wave we get 6 output pulses. Alright. So, that is known as 6 pulse rectifier. Okay. Similarly, there are 12 pulse, 24 pulse, 48 pulse and 96 pulse rectifiers similarly. So, and you are also observing that as soon as the pulse number is increasing, the time period is decreasing. Here when it is 1 pulse rectifier, the time period is same as input, but when it is 2 pulse rectifier, the time period becomes half. Alright. So, when we go for the 3 pulse rectifier, time period will become 1/3 of the input, and when you go for 6 pulse, the time period will become 1/6 of the input. So, that is the meaning of this pulse number. Alright. And B represents the connection type, B means bridge type connection, and M represents the midpoint type connection. Alright. So, in general we have all studied that generally we do not go for the midpoint type rectifiers because of several disadvantages such as less transformer utilization factors, and you need a tapped transformer for that, which is not considered very good even when we are going for the high voltage high current circuits, all right, and several other things. But the one advantage which it carries, with the midpoint type rectifier carries, is that it means you do not have to synchronize the two switches, because in one cycle only one switch is applicable, all right. So, if you see the connection of midpoint type, so the midpoint type of connection is like this. You need a 1:1 transformer like that, and the devices are connected like that, and load is connected in between the tapped transformer like that. Okay. So, this is my reference load voltage, reference load current like this. So, that is the main disadvantage here, you need a tapped transformer. So, which is very costly affair when you are going for a high voltage circuit, all right. So, but if you go for the bridge connection, so bridge connection is like this, you need 4 devices to make a H bridge like this. Oh, sorry. So, this is the connection and this is the load. So, this is let us say here it is D1 and D2, here it is D1, D2, D3, D2 and D4. So, you can see that here, and this is the load voltage reference and load current reference. Similarly, source voltage reference and source current reference. So, you can see the difference between these two, that for a bridge connection you do not require a transformer at all right. But the main disadvantage with bridge rectifiers is that since we know that the two power semiconductor devices are never same, if you talk about the practical devices, they are never same in their characteristics, especially dynamic characteristics, all right. One device may turn on slower and one device may turn on faster, similarly for turn off also. So, that there may be some mismatch also. So, for matching that we need some additional circuits, all right. But that disadvantage is not as big as the advantages it provides us, all right. Here if you talk about the diode ratings, you needed twice net PIV rating of diodes. For if the same VM, you are providing, Vs is equal to Vm sin omega t, and here also we are providing Vs is equal to Vm sin omega t, then this here the devices require PIV rating of 2 Vm, but here the devices require the PIV rating of only Vm. How is it that we are going to see in further in this lecture, all right. So, these are the advantages. So, but the output and the other workings remains the same, only the difference is in the device voltages and device currents, all right. So, now let us move on to the topic for single phase. First I am explaining single phase half wave rectifier, and then with the analogy to the I am explaining single phase full wave uncontrolled rectifier, then with the analogy to the full wave rectifier uncontrolled type, we will go with the full wave controlled rectifiers. So, that is now I am considering B2 type B2 rectifiers. Now, you understand what is B2, all right. Bridge type 2 pulse rectifiers, uncontrolled type, with various types of load. Okay. So, here if you see here like this, let us have a B2 connection again here. These are my connections. diodes and here is my load, which may be R load, RL load or RLE type load, whatever is there. Okay. So, let us say this is my load voltage reference, again I am taking to terminal to terminal, this is load current reference, this is source voltage reference, this is source current reference, and similarly you can draw any of the diodes or any of the diode current and voltages. I am making only one VD1 and its reference ID1. So, this is diode D1, this is D3, this is D2 and this is D4. So, here let me tell you something that in this, when you come to the bridge connections, first of all you see that the upper group, there are I am now just marking something. You see here I have purposefully marked upper group as odd numbered. Okay. So, you see here this upper group is known as positive group and this lower group which is marked purposefully as even numbered is called known as negative group, or in other technical terms it is known as the upper group or positive group is known as common cathode connection and the lower group is known as common anode connection. Alright. So, here how it is, so you see in the first group you see that both the anodes of the diodes are at different potentials, but both the cathodes of the upper group are shorted together. That is why the cathodes of both the diodes are at same potential, that is why it is known as common cathode connection. But if you go for the lower group, you see here that both the diodes have cathodes at different potential, but both the diodes have the anode at common potential. Alright, that is why it is known as common anode type, and this is called common cathode type. So, here just learn the concept here, because this concept is applicable for the 3 phase. If you learn it here, then only you can apply it for the 3 phase. Alright. So, what the concept is that when at any particular instant, please note that when at any particular instant, because we are analyzing the devices instant wise, power electronic circuit instant wise. So, when at any particular instant the means if you talk about the positive group, the voltage when means in positive group, when the diodes become forward biased, means the most the diode which will be most forward biased, means at any particular instant. If you talk about the positive group, in positive group, ठीक है ना, the most positive diode will become forward biased, the most positive diode or switch, because this is equally applicable for others also. So, most positive diode or SCR becomes, the most positive diode or SCR becomes forward biased, and in negative group the most negative diode or SCR or switch will become forward biased, SCR will become forward biased. So, you see here when there is common anode type connection, so both the anodes are at ground potential or say 0 potential. So, the potential of cathodes which must be negative decides which diode will turn on or which thyristor will turn on. Similarly, in the positive group, both cathodes are at 0 potential or same potential. So, the potential of anodes which is more positive will decide which diode will turn on. This concept, if you learn here, this concept will help you with the 3 phase circuits. Alright, because you might have learned in your previous university studies that since when positive cycle is coming, so we say that here plus is here, plus either plus is here, minus is here, minus is here. So, this is plus, this is minus. So, this is reverse bias, this is reverse bias, this is forward bias. Okay, this concept is all right for understanding this circuit. All right, but this plus plus minus minus concept is not good when you are going for the 3-phase circuits, because in 3-phase waveforms at any instant any 2 waveforms are positive and one is negative, or at another instant any 2 waveforms are negative and one is positive. So, how can you decide plus plus and minus minus? You will become confused that which device is going to be turned on. All right, because both are positive. So, that is why this is important to learn that in positive group the most positive diode or SCR will turn on, and in negative group the most negative diode or SCR will become turned on. And when both groups conduct simultaneously, when switches of both groups conduct simultaneously at any instant, then output is available. All right. So, it is compulsory that one switch must be turned on from the positive group and one switch must be turned on from the negative group, whether it may be diode or it may be SCR. That is why I am not quoting diode or SCR, I am quoting as switch. All right. So, one switch must be turned on from the positive side and one switch must be turned on from the negative group in order to have a output voltage or output current at the load. All right. If you turn on both the switches of same group, you will get nothing. All right, and it is not possible also. All right, but if somehow other, if you turn on both the switches of the either of the positive group or either of the negative group, then what will happen? The source will become short circuit. Suppose if you turn on D1 and D3 by somehow other, by hook or crook, if you turn on D1 and D3 simultaneously, what will happen? The source will become short circuited. So, this should not come. All right, but if you turn on the both the switches from the same leg, which we will see later in the lecture, in the coming lecture, subsequent lectures, that if you turn on both the switches of the same leg, then you will see that the source is disconnected, because suppose D1 and D2 are turned on simultaneously, then obviously D3 and D4 will not be turned on. All right, in that case what will happen? This leg will be short circuited and the source and load are disconnected. All right, in that case source and load are disconnected. So, let us start with the analysis of the circuit. So, if we want to analyze the circuit, let us start with our basic one, that is with resistive load. So, very simple circuit is there. So, this is full wave rectifier, uncontrolled type. We have got source here and this is D1, D3, D2, D4. It is not necessary that you have to keep the same numbering. You may put D positive or DA positive, DA2 positive, or DA negative, DA2 negative, like that also, whatever you need, whatever you like to be. So, R load is here, this is output reference, this is output current reference, this is source voltage reference, this is source current reference, and let me take any of the diodes, let us say it is D1 reference and ID1 reference. Okay. So, now start with the waveforms. So, this is our source voltage. Okay, let's mark the instants 0, pi, 2 pi, 3 pi, 4 pi and so on. This is my load voltage. Okay, so this is the load voltage. Now, here we have to draw many things. I have already told you this, that as soon as we go for the more complex circuits, more waveforms can be added. So, you have to learn the concept, not you have to cram anything. So, let us say this is load current. Now, let us say let me draw also other currents also. Let us say I have to draw the source current also. Let us say I have to draw the diode current also. Let us say diode 1 current I am drawing, okay, ID1, and let us say I have to draw the load voltage also, sorry, not load voltage, this diode 1 voltage. Okay. So, I am drawing VD1 voltage also. So, this much we can draw. Even if you want to add some more, you can draw the diode 3 voltage, diode 2 voltage, diode 4 voltage and their subsequent currents also. So, the number of waveforms could increase to very large values, So, now let us start its analysis. So, starting it with the instant wise. So, if you talk about from 0 to pi, first instant we are taking from 0 to pi. From 0 to pi, if you take, from 0 to pi, what will happen? See, from 0 to pi, what is happening? You see that diode means the supply is like this. See, that is the supply. Means if I mark it here, the positive side is here and negative side is here. Now, you have to apply this concept which I have just told you, that what is the most positive diode in positive group and what is the most negative diode in negative group. So, if you see here in positive group, for this supply value, diode D1 is more positive, and in negative group diode D4 is most negative. You can see with the waveforms. Alright, how that if positive is there, so this positive voltage will be at this bus at this point and this negative voltage will be at this point. Okay. So, what will happen? So, positive voltage is this at this bus, it means that this diode will become, its cathode will become positive and its cathode will become negative, and here its anode will become positive and its anode will become negative. So, among these two, diode D1 is most positive, and among these two the diode D4 is most negative. So, from instant 0 to pi, diode D1 and diode D4 will turn on. I hope you understand this concept with this what I have told you here. All right. So, when you apply here this diodes values here, so what you see that diode D1 and D4 are on and diode D2 and D3 are off. So, second step is let us draw the modified circuit. If you draw the modified circuit, what you will get here? You please see. Let us draw it first. So, at the learning stage, it is very nice to draw these circuits again and again, and when you become expert, then there is no need. You just by observing you can see that which will be on and which will be off and what will be the circuit conditions. All right. So, it will be like this, and here it is the load. which is a resistance, and these are my references I naught and V naught, these are my references. So, now connect it, what you see, what you observe here. So, what you are observing here, this is Vs and this is Is with this references. So, what you are observing here, when you see that since this is short circuited and this is short circuited, this is open circuited, this is open circuited. So, if you try to modify even this circuit also, if you try to modify, what you can see that this point is A. So, this point is also A and this point is also A, this point is also A and this point is also A, and if this point is B, this point is also B, this point is also B and this point is also B. So, what do you see that this A point is in parallel with this A point and this B point is in parallel with this B point, means again you can see that the load voltage is parallel with the source voltage. Let us again remodify this circuit. Okay, let me remove these open circuit branches and let me short these short circuit branches. So, if you draw it like that, so you can draw the circuit like this. So, this A can be brought here and this B can be brought here. So, if you draw it like this, you see. Now, I think you can very clearly see it, that how the load voltage is in parallel with the source voltage. See here, load voltage is again in parallel with the source voltage. So, whatever the source voltage will be there, that will appear across the load, means a sine wave from 0 to pi will be appearing with of same magnitude Vm and Vm. All right. So, now if you talk about the load current during this instant, so you see that this is Is. So, the load current is flowing here, Is and Is are series, and load, since it is resistive load, hence the same nature of current will be there as that of voltage. The amplitude may either scale up or scale down depending on the value of resistance. So, it value peak will be Vm by R. Now, if you draw the source current, yes, source current is also there. Now, you see that the source current reference is when it is exiting from the source. All right. So, here also you can see that the source current is exiting. So, it is following the reference, that is why the source current is also positive and same as that of load current, because it is in series, same Vm by R. And if you want to draw the diode current, you see here diode D1 and D4 are turned on. So, if you see here in this circuit here, you see that this is diode D1 and source current is going from D1 to load and then D4 and again back to the source. So, again the Is, ID1 and I naught are same. So, again the ID1 will also be same as source current, load current. So, its value will also be Vm by R. And what is the diode 1 voltage? You can see diode 1 is on. So, when the diode is on, obviously the output voltage will be the voltage across diode will be 0, because it is short circuited. All right. So, now move on to the next instant, that is from pi to 2 pi. So, when you move from pi to 2 pi, what is happening here? Now, you see, now the supply has become like this. Okay. So, when the supply has become like this, it means this supply, this cycle was positive for some pair of devices, and again this cycle, although with our 0 reference, it is known as negative cycle, but for some devices it will act like a positive. All right. So, here if you draw it, if you see here, so when the cycle become like this, let me draw it with some other color like this. So, when the cycle is becoming less, minus here and plus here, what is happening here? So, here at this bus, now minus is appearing and at this bus plus is appearing. See here. Okay. So, here minus is appearing, here plus is appearing. So, you see that its anode is at negative potential, its cathode is at negative potential. D1's anode is at negative potential and D2's cathode is at negative potential, and D3's anode is at positive potential and D4's cathode is at positive potential. So, for D1 and D3 we need a higher potential values or positive, most positive. So, here you can see that D3 is most positive, and in negative group we need most negative. So, here you can see that D2 is most negative compared to D4. So, obviously, during the instant of pi to 2 pi, D3 and D2 will be forward biased. all right. So, we can write here that D2, D3 are on and D4, D1 and D4 are off. So, now if you draw the modified circuit like this, just like this we have drawn. So, if you draw the modified circuit, we can draw it like this, you can see. Load is connected here, resistance, the output voltage reference, output current reference, source connected here and one here. So, here you can see D1, D3, D2, D4 and now the supply is like this, you can see, but we have yes and they sorry, we have to draw the references. The supply is references here, I am drawing references here, but what is the actual value of supply here? You can see the actually supply has become this, all right. That is why with respect to 0 reference, we are saying that this supply is negative. Okay. So, now you can see that if you see here that this current from here it will go like this, now like this it will go, the source current will go like this, it will pass from D3 and then this, here you follow, you see that the load voltage and load current references is still followed. You see that you just trace the path, this is the value of supply plus here minus here, and so the current source current is going like that and it is going like this, going from D3 to load. So, when it is going from load, again you see the load current and load voltage references followed. So, when the load current voltage references followed means the load voltage and load current both are positive, and again it will go to D2 and then back to source. Now, here you see, now here instead of getting means getting out from the source from this side, it is getting in the source from this side. So, here you can see the source current will become negative, all right. So, we will come to the source current later. First of all, let us draw the load voltage and load current. So, you can see that load voltage is positive and load current is positive, and since it is resistive load, again you can see that the load is again in parallel with the source. How you can see that? Just remove these open circuited terminals and bring the short circuited terminals to whatever there. Bring this terminal here and bring this terminal here. So, if you bring it like that, what you will get? You see here, let us say if it is A terminal and if it is B terminal, you see that what is happening. This A terminal is going to this side here and the B terminal going to this side here, and the supply is like this basically. Sorry, yes, this supply is going here like this, and this supply negative 1 is going here like this. Okay, see. So, plus is going here and minus is going here. So, again you can see that the load voltage is in parallel with the source voltage. So, when the load voltage is in parallel with the source voltage, again the output will follow the source, all right. So, again we will get the output as like this sine wave, and since it is resistive load, as the load current will also be same sine wave. Now, you have to draw the source current. So, here you can see that instead of getting here, instead of getting out source current from here, we are getting source current in from here. You see here this one, all right. The source current is getting inside at this side, but what is the reference? That source current must go outside in the red one you can see. alright. So, it means that the source current is flowing opposite to that of reference. So, it means, but source current and load current both are in series, it is a series, you can see that they are same. So, it means that whatever load current is there, that will flow in the source, but negative side, but negative side. Okay. So, it is flowing negative side. So, same here it is also V m by R. So, here also it is V m by R. And now, if you want to trace diode 1 current, so here you can see that diode 1 current will be 0, because diode 1 is off. Okay. And what is diode 1 voltage? Here diode 1 is also off. So, if you want to calculate the diode voltages, again we have to write the KVL equations. So, if you write the KVL equations here, just write it, you will get, here it is plus reference, it is minus reference, you write it, you are going from here, let us write it Vs minus Vd1, and from here from Vd1 we go with the V naught and then minus this Vd4. Okay, you see here Vs minus Vd1 and then just remove these branches, okay, like this. Okay. So, Vs minus Vd1 minus V naught equal to minus Vd 4 also minus V naught equal to 0. So, you can see that what is the value of Vd1? It is like this, Vs minus V naught, all right, and Vd4 also he is here. So, here if you see that Vd1 voltage will be basically same as that of here, because here if you try to write Vd4 also, you can see that both are in parallel. If you try to draw the circuit here, let me make the circuit here like this, or let me take a modified good circuit. Yes, let me make here. So, this is open circuited, like that. Like that it is, all right. So, when you draw it or when you draw it, you will get what is the value of Vd here, it is equal to Vs minus V naught. Okay. So, when you get its value, the value of Vd1 will be the source voltage across it. Okay. Here you can, because you can see here that the load voltage is something flowing from this one, from here, okay. Or in other way you can understand in even more simpler way. Let us understand in even more simpler way. Okay. Let us remove all this, even in more simpler way we can understand it. Here you can see that since this is short circuited, here it is. So, you can see if you draw the circuit here. So, because of this short circuiting here, this point will come here, all right. So, this point will come here, all right, and because of this point is here already. So, here you can see that this plus is coming here and this minus is already here. So, what you can see that the diode voltage is parallel with this supply voltage, you see here. So, here it is plus and it is minus, but our reference is plus here, minus here. See, our reference is here, because if you take reference as plus minus, so it must be like that, but we are getting like this, like this. Okay. So, here you can see that if you want to make the diode 1 voltage, it is equal to source value. So, the diode 1 voltage will equal to source value, and source value is acting negative for this diode 1 voltage. So, hence we have got this value. alright. So, its value will be Vm. It means you need a diode of PIV rating of Vm, alright. So, again moving on to the next instant, that is from 2 pi to 3 pi. Again at 2 pi to 3 pi, you can see that diode D1 and D4 will be on and D2 and D3 will be off. So, because of that, what will happen? Again the voltage will be positive because D1 and D4 are on. So, what we will get here, that this circuit will get, alright. So, again you will get output voltage like this and output current like this. Again source current will be positive because source current will follow the reference, and diode 1 current will be like this because diode 1 is on and diode 1 voltage will be 0. So, we have seen, and again when you move to the next from 3 pi to 4 pi, again the the instant is like this, means D3 and D2 are on and D1 and D4 are off. Then the output will again be positive, load current will also be positive, but source current will be negative because it is flowing opposite to that of reference. Diode 1 is off, so that its value will be 0, current value 0, and diode 1 is off, hence voltage across it will be Vm. Okay. So, in this way you can go on continue the waveforms of single phase uncontrolled rectifier with resistance load. So, now if you want to find out the average output voltage and RMS output voltage, you can see that its time period is pi, take any value, time period is pi. So, I am just writing it directly, you have to prove it, that V naught average, its value will be 2 Vm over pi and its RMS value will be Vm by root 2. You have to answer this question in the comment section, why it is Vm by root 2. Means for a full wave rectifier, why we are getting RMS value of output voltage as Vm by root 2, which is also the RMS value of a sine wave. You have to answer this in the comment section. It is very basic, you have already studied it in the basic electrical engineering. If you know the definition of RMS, root mean square, then you can easily answer that, alright. So, now let us move on to the further. Now, I am doing one thing, I am explaining the controlled circuit also with this along with this uncontrolled circuit. So, let me move with a single phase controlled rectifier with R load, alright. If you have understood the uncontrolled one, you can easily understand the controlled one also. So, if we draw single phase controlled rectifier, so, instead of diodes, we have got SCRs or resistive load. These are my references, V naught, I naught, T1, T3, T2, T4. This is source voltage reference Vs and Is. Similarly, you can draw voltage across any thyristor VT1 and current through any thyristor IT1. Okay. The working is same as that we have learned in the diode section. The only difference comes is that, means in case of diode you have got instantaneous turn on and instantaneous turn off as soon as the diode is forward biased or reverse biased, but in case of thyristor it is not the case. The thyristor will not turn on until unless you provide the gate pulse or the triggering pulse to the SCR. Because of this only difference will come, and that is why again I have already explained this in my previous lecture also, that because with the use of thyristors we can control the phase of any input sine wave. That is why they are also known as phase controlled rectifiers. alright. This is the reason why they are called as phase control rectifiers also, because you can easily control the phase of any means input sine wave, alright. Previously we were able, before the advent of thyristors, we were using the thyrotron tubes, and with that to some extent we are able to control the phase, but not to much extent, alright. But here we can very smoothly control the phase. Even if you want to control the phase in decimal of the degrees, let us say you want to control it 0.1 degree, 0.2 degree, even that is also possible with these circuits with the advent of thyristors, alright. And ultimately you can be able to control the average value. But before the advent of thyristors or thyrotron tubes, the only way possible to control the average output voltage is to either step up or is through controlling the amplitude of the wave, means which requires the use of transformers, alright. But that was a very costly and very heavy affair, and also limits this very of the advantages. So, now here this is my pi 2 pi, black margin is showing the multiple of pi instants, and let me show the thyristor triggering angles also here. So, let us say this is the triggering angle alpha, okay. So, now you have to remember that in half wave only in the in one half cycle I have provided only the positive half cycle, I have provided the firing angle. But when you come to the full wave rectifiers, I have told you early in this lecture only that this sine wave, the half portion of this sine wave will act like positive cycle to some pair of device, and another half wave of the sine wave will act as positive to another pair of device. That is why I am putting a firing angle here also. You please note that this firing angle which I am showing downwards, it is not negative. You please note this. This is not negative voltage of firing angle. No, it is positive one, but I am showing it here because to make you understand that this wave is positive for the other pair of devices. Hence, for that pair of devices, the positive firing angle is provided to that pair of devices, like that. And the similar concept that is applicable, that in positive cycle means in any instant, whatever device is most positive in the positive group and whatever device is most negative in the negative group, that will switch on. So, here we have got alpha, alpha plus pi, then again alpha, and we provide symmetrical firing. You please note it. Symmetrical firing means that whatever firing angle you are providing in the positive cycle, that similar firing angle you are providing in the negative cycle also, alright. It is not that in the positive cycle you are providing, let us say alpha 1 degrees and you are providing alpha 2 degrees in the negative half cycle. No, we are providing the symmetrical firing, alright, because symmetrical firing helps us to avoid unnecessary harmonics in the power electronic circuits and unnecessary harmonics in the PCC. PCC is where point of common coupling basically. You will study what is PCC in power systems. So, these red one markings are basically the firing angles. Alright. So, let us draw the output voltage, let us draw the output current, let us draw source current, let us draw any thyristor current. I am drawing here a VT1. You please practice with other thyristor currents also, you may practice with IT2 or something, alright, and let us draw the thyristor voltage also. Okay. So, here we have got thyristor 1 voltage. Okay. So, now you see that if you talk from 0 to alpha instant, so what is happening here? You see here from 0 to alpha what is happening? These thyristor T1 and T4 are positive. Now, I am not explaining in detail why they are positive. I have already explained with the diodes. So, now I hope that you have learned it, how it is. So, the thyristors T1 and T4 are forward biased and T3 and T2 are reverse biased. So, forget about T1 and T2 and T3, let me write it here. T2, T3 reverse biased means off, and T1 and T2 forward biased but is still off. Why it is still off? Because until unless because it is not diode, so it is thyristor. Until unless you do not provide firing angle of gate pulse to the thyristor, it will not turn on. All right. So till the point you do not provide the gate pulse to both the thyristors simultaneously. Here you have to note that now you have to provide the gate pulse simultaneously to the all forward devices. All right, you cannot delay. All right. So now when you provide the gate pulses simultaneously to the thyristor, then only they will turn on. All right. So here you can see that T1 and T2 are forward biased, but it's still off condition. So you can see all 4 thyristors are off. It means the circuit load is disconnected from the source. You can see that all the 4 are disconnected. All right. If you draw the modified circuit, it will be like this. Like that. Okay. So all 4 are disconnected. So hence no load is disconnected from the source, and the output voltage will be 0. Output current will be 0, source current will be 0, thyristor currents will be 0, but thyristor voltage will appear. Now here what thyristor voltage will appear? Again take reference from this circuit, from where we have drawn the diode voltage. So here you can see when the thyristor is off, you see that this voltage, source voltage, appear across the T1 and across the T4, and this, since both are T1 and T4 are not T2. So T1 and T4, it means what? Whatever the source voltage is appearing, that is appearing across the T1 and T4, and both of them since are forward biased, hence the positive voltage must be appearing. If the negative voltage is appearing, that they should not be forward biased, they must be reverse biased. All right, but they are forward biased, it means positive voltage is appearing across both of them, means the positive cycle of this sine wave will be appearing across the T1 and T4 like that. Okay. But what is happening when second instant comes, alpha to pi, what will happen? At alpha, as soon as you provide the gate pulse to the T1 and T4, both the thyristors will turn on immediately, and the load and source are again connected, and the circuit will be like this, which we have explained earlier, which I have explained earlier, which I have discussed earlier. All right. So when the circuit is like this, again the load is in parallel with the source, but load becomes parallel at alpha instant, means at alpha instant the source has already reached to this point. So load will follow the output from this point, hence the load will be, voltage will be a clipped sine wave like that. Okay. And since it is a resistive load, hence the output current will also be same like this. Okay. And what is the source current? You can see that the source current will follow the reference source current, and it will also be same as load current, shape will be same as load current, as well as direction will also be positive. It is Vm by R, Vm by R. And what is the thyristor 1 current? It is also positive and same as load current, and thyristor voltage, because thyristor 1 is now on, it will be 0 thyristor voltage. Now let us talk about from pi to alpha plus pi instant. So here you can see that now the T1 and T4 are on. Okay. And now from pi to alpha plus pi, if you see what you are observing here, that here the thyristor T1 and T4 are reverse biased and thus off, no problem with that. Okay. And when you see for the T2 and T3, so with the concept of same, most positive will be turned on in positive group and most negative will turn on in negative group. So here you can see that T2 and T3 will become more reverse forward biased from pi to alpha plus pi, means during this instant, during these instant. So this T2 and T3 will be forward biased, but they will not be on, they will, because the gate pulse is not available to them. Hence again all the 4 thyristors are disconnected, all the 4s are thyristors are off, hence the load is disconnected from the source. So, circuit will be like this, hence the output voltage will be 0, current will be 0, source voltage will be 0, and thyristor 1 current will be 0. Thyristor 1 now it's reverse bias. See, the thyristor 1 is reverse bias, means the reverse sign will be appearing across it. All right. So, since I am analyzing till this point, so I am drawing till this point. Now, what is happening from alpha plus pi to 2 pi? What is happening there? So, if you see here, now here the T2 and T3, as soon as at alpha plus pi you provide the gate pulse, now you see that T2 and T3 will be they are already forward biased. As soon as they get the gate pulse, they will come to the forward conduction mode, means they will become short circuited switch, and as soon as they become short circuited switch, again the circuit will be like this one, which we have drawn in the diode case. All right. So, now in this case circuit will be like this. Again you see that when the T2 and T3 are on, you see that the supply is not this. So, supply is this. So, the current will go like this from here to T3 to load, and then load to T2 and T2 to back to supply. So, here you can see the load voltage references again followed and load current references again followed. Hence, again the load is parallel with the source and for references followed, hence it is positive. All right, and current will also be positive, load current. But if you see the source, you see instead of going outward, the source current getting is inward in this circuit. So, here the source current will be same shape, but negative side like this. Okay, same shape, but negative side, and since thyristor 1 is reverse biased, its current will be 0, and full cycle voltage, full negative cycle voltage will be appearing across thyristor voltage, which I already explained with the diode also. So, if you have understood with the diode, you can very easily understand with the thyristor also. Again, if you come to the 2 pi to alpha plus 2 pi, this seems, if you see this 2 pi to alpha plus 2 pi, this is same as 0 to alpha instant. So, again all the again the T1 and T4 are forward biased, but in the blocking mode, and T2 T3 are reverse biased, hence they are already off. So, all 4 thyristors are off, hence the output voltage is 0, output current is 0, source current 0, thyristor 1 current 0, thyristor 1 voltage is positive sine wave. Okay. And at alpha plus 2 pi to 3 pi is same as alpha to pi instant. So, at alpha plus 2 pi, the resistors T1 and T4 will get the gate pulse and they will be on, hence the output voltage will appear like that, and output current will be like this. Source current is following the reference and it will be like this, and thyristor current will also be like load current like this, but thyristor 1 voltage will be 0 because it is short circuited. Again 3 pi to alpha plus 3 pi is same as pi to alpha plus pi instant, and at this point T3 and T2 are forward biased, T1 and T4 are reverse biased, but all 4 thyristors are off, T1 T4 due to reverse biasing and T2 T3 due to forward conduction mode because of absence of gate pulse, hence the output voltage will be 0, output current will be 0, source current will be 0, thyristor 1 current 0, but thyristor 1 is reverse bias, hence reverse voltage will apply here. All right, and from alpha plus 3 pi to 4 pi again you go. So, it is same as alpha plus pi to 2 pi instant. All right, in this case the T2 and T3 are getting the gate pulse and they will become immediately forward conduction mode thyristors, and again the load is connected with the source and it will follow the source like this, and output will be like voltage like with this, and output current will be like this. And source current will be negative now because T2 T3 are on. All right, shape is same but negative direction. Thyristor 1 is off, so its value current will be 0 and full negative voltage will be appearing across it. So, what is the PIV rating of thyristor? It is Vm. So, PIV rating of thyristor in this case is Vm. Okay, and in this way the circuit will go on. Now, one more question in with the full wave comes, that what is the firing angle range? Firing angle range. Firing angle range means from which value to which value your device will remain forward biased so that you can fire it. That defines the firing angle range. Alright, it is not necessary that the firing angle range will always remain 0 to pi. No, the firing angle range will remain from that to that point, from where the thyristor will remain means will start to be forward biased and will remain forward biased till that point. Alright. So, if you see in this circuit, for any thyristor, the thyristor is becoming like, if you say about T1 and T2, the thyristor, sorry, T1 and T4, they are forward biased from 0 to pi. That's hence the firing angle range is 0 to, not 0 to pi, basically it's from 0 to pi. It means that firing angle range is pi radians, means from alpha equal to 0 to alpha equal to pi, you can fire the SCR. Alright. Similarly, is for the T2 and T3. So, here in the case of full wave controlled rectifier with R load, your firing angle range of thyristor comes out to be 0 to pi. Again, I am defining how we calculate firing angle range is that from which point, from initial point from where the thyristor starts to become forward biased and to the end point, to that point till that thyristor remains forward biased, so that we can provide the firing angle is known as firing angle range. You can see that if you want to provide firing to the thyristor 1 after pi, it is not possible. Why it is not possible? Because thyristor 1 becomes reverse biased after pi. Alright, that is why the firing angle range for all the thyristors is 0 to pi. So, in this lecture, now you have to find out the average output voltage. I am writing it here, you have to calculate it. Its value is Vm upon pi 1 plus cos alpha. Now, how to check it? I have already told you that you have to check it with the general or very basic case of diode with resistance. So, if you see very basic case of diode with resistance, then alpha must be 0. Alright. So, if alpha is 0, then you see cos 0 is 1, 1 plus 1 2, 2 Vm upon pi you get, and 2 Vm upon pi we get with the diode case. Alright. So, hence this value is correct. So, now you have to find the RMS value of output voltage, calculate it, and please put the answer of these two questions, V naught RMS in case of controlled rectifier, and this question of why in case of diode rectifier, why the output RMS value of output voltage is Vm by root 2. Please answer these two questions in the comment sections, and for any queries and doubt and how do you like the lecture, please also post that in the comment section, and for your doubt clarification sections, please join our Telegram group. Till then, thank you very much.